We are on Unit 2, Notes 4. This section is on derivatives of exponential functions. So I'd like to begin first with this section asking ourselves, what is an exponential function? Because sometimes there is a little confusion on that. What determines, what makes up an exponential function? So let's take a look. If we had f of x is equal to 3x to the fourth, is that exponential? I see an exponent, so is that exponential? The answer is no. This is not considered an exponential function. This is a polynomial function. Okay? What about 4x to the negative 3? Is that an exponential function? No, this is not. This is actually a rational function because it would be 1 over x cubed, right? So that would be called a rational function. Okay, in both of these, the power rule applies for derivatives. To find the derivative, both of those would be power rule, but neither of them is exponential. Okay, for an exponential function, here's an example of an exponential function. F of x is 2 to the x. Here's another one. G of x is 3 times 4 to the x, or negative 5e to the 3x squared. Okay, these are exponential functions. Okay, they're exponential because the variable is the exponent or is part of the exponent. Okay, that's what makes it an exponential function. Now what's crucial that you know here is that the power rule does not apply for derivatives, okay? Does not apply. If you're finding the derivative of this, do not try to use some power rule on that, okay? Yeah, we have to do something else, all right? All right. Before we get there, though, let's do a little bit of a review with exponential functions. Let's start by solving some equations. So let's solve for x. A couple of little examples. So if we have 5e to the 3x plus 1 plus 3 is equal to 20, let's solve for x. First, we're going to isolate the exponential function. So subtract 3 from each side. Then divide by 5. So e to the 3x plus 1 would be 17 over 5. So isolate your exponential function and then ln both sides. ln both sides. What happens when you ln this? Well, the exponent we can pull out to the coefficient, and then you have ln of e, and ln of e is just 1. So this is just your coefficient. Okay, and now finish solving for x. So subtract 1, divide by 3. So ln of 17/5 minus 1 all over 3. Okay, that's a little 5 there. Okay. What about this example? What if we have 9 times the natural log of the cube root of x plus 1 is equal to 4? What if we have this and we want to solve for x? Well, the first thing I would do is I would pull this is x plus 1 to the 1/3, and I would pull that 1/3 out in front. So I'd have 9 times 1/3 ln x plus 1. That's what I would do first. We could have divided by 9 first if we wanted to, but this is what I would do. So then we have 3 out here. I'm going to divide both sides by 3. So we have this. So we have isolated the log. Isolate the exponential or isolate the log. And now I'm going to e to both sides. E to the left, e to the right. Whole side. E to the ln of x plus 1 is just x plus 1. E to the 4/3 is e to the 4/3. And now just subtract 1. And you're done. Okay, so isolate, and then either take natural log of both sides or e to both sides, and then finish up. Okay. What does the graph of y equals e to the x look like? Y equals e to the x. The graph looks like this. So e to the 0, when x is 0, e to 0 is 1, so that's 1. E to the 1 is e, so when x is 1, we're up here at e, so 1e right there. Okay? So that is what the graph of y equals e to the x looks like. A couple things about this graph. Let's see. The limit as x goes to infinity of e to the x is definitely infinity. It definitely goes to infinity. It goes to infinity very quickly. Very, very quickly. Okay? The graph is continuous for all x. No holes, no breaks, no asymptotes, no nothing. It's continuous. All right? It's also differentiable. We didn't say that about natural log, but it is also differentiable for all x. Can find the derivative. It's increasing for all x. So the graph is the next y value is always higher than the previous y value. It's increasing. This graph is concave up for all x. The slope is always increasing. That means it's concave up. The slope is always increasing. The slope. It's always increasing. Also, concave up is part of a smile. Part of a smile. Do you agree that that's part of a smile? Yes. Okay. And it's another one-to-one graph. Passes both the vertical and the horizontal line test, so it's 1-to-1. Which implies that the its inverse is also a function. Well, let's talk about this inverse, because we have the graph of e to the x that looks like this, and we have the graph of natural log x, which looks like that. Right? These two are inverses of each other. They are reflections of each other through the line y equals x. So this is y equals ln x. This is y equals e to the x. Okay? And they're reflections of each other. That means that they're points, they have corresponding points. The point 1, 0 is on ln x, so the point 0, 1 has to be on y to the e to the x. The point E1 is on ln x, so the point 1e is on e to the x. They're corresponding points, okay? So they're inverses of each other. All right, we'll be talking more about inverses in our next section. Okay. All right, so a little quick review of exponentials. Now let's talk about derivatives. All right, derivatives of exponential functions. All right, very important. Do not use the power rule for exponential functions. If you have f of x is x cubed, yes, that is power rule. So f prime would be 3x squared. power rule. But if you have g of x is 3 to the x, do not try to use some form of the power rule on that, okay? G prime of x is not x 3 to the x minus 1. Does not work that way, okay? Don't try to do that. If you do that, I'll be very sad, okay? Don't do it. All right, so if it's not that, what is it? Well, just like with logs, we looked at natural logs first. With exponentials, we're going to look at e to the x first. So let's consider y equals e to the x. Okay, let's consider that. And we want to find dy dx. Okay, I'm going to show you why the formula is the way it is. Okay, all right, so I'm going to begin with this little equation, and I'm going to ln both sides. I'm going to ln both sides. So I'll have ln of y is ln of e to the x. ln both sides. Now I have ln of y is equal to, I'm going to move the exponent to the coefficient, and then I'll be left with ln of e, which is just 1, so this is just x, right? Okay. I want dy dx. Now I can find dy dx because I know what the derivative of natural log is. So now I'm going to take the derivative of both sides with respect to x, because I want dy dx. Okay. The derivative with respect to x of ln y is 1 over y dy dx. A little implicit differentiation there, right? The derivative of x with respect to x is 1. So dy dx, if I multiply both sides by y, dy dx is equal to y. Well, what was y? Y is e to the x. So dy dx is e to the x. So if y is e to the x, dy dx is also e to the x. Not very many functions are derivatives of each other, or of themselves, I should say. And you might be thinking, gosh, is that really true? Let's find out. Let's find out. Let's confirm, okay? So supposedly, if we have e to the x, that's the same thing as the derivative of e to the x. So let's find out. Math 8 with respect to x of e to the x, evaluated at every x that it comes across. So let's see. I'm going to zoom for. There's e to the x. Not a surprise. We knew what that looked like. And it looks like nothing else graphed. It's still going. It takes a little while to graph a derivative. Okay, it's done. It's done, but it looks like nothing else graphed. Did anything else graph? Well, of course it did. If we trace, here we are at e to the x. If I go down to the other graph, look at, does the y change as I go up and down? Does the y change? It does, but very, very slightly, and that's just that error in the numerical derivative that it's finding, okay? So this is true. So the derivative with respect to x of e to the x is e to the x. Okay, what if we have the derivative with respect to x of some other variable? Then we use implicit differentiation. So e to the u times du dx, right? Which we can think of as u prime e to the u. Okay? All right, well, what if we don't have e to the u? What if we have a to the u? What if we have some other, should we make it x? I'll do x first. Okay, where a is a constant. So 2 to the x, 3 to the x, something other than e to the x, all right? Well, let's do the same thing. Let's take ln of both sides. So we'll have ln of y is x ln of a. This time that's not just 1, so we have to write it as ln a. But ln of a is just another constant, right? So I could think of it as being out in front. It's like a 5x or 10x. It's just ln a times x, right? Now let's take the derivative of both sides with respect to x. We'll have 1 over y dy dx is equal to this constant I'm just leaving there, and then the derivative with respect to x of x is just 1. So dy dx is ln of a times y, which is a to the x. All right? So the derivative with respect to x of a to the x, where a is a constant, is ln of a times a to the x. What if you have a u? Same thing, except at the end you'll have a u prime or a du dx. So I'm going to write the u prime out front, ln a to the x. All right? Things to know. Put it in your memory banks. Okay, let's look at some examples. Example 1, f of x is e to the 5x cubed. Okay, what is the derivative? F prime is the exact same thing times the derivative of the exponent. Well, the derivative of the exponent is 15x squared, and then I write that e to the 5x cubed. That is the derivative. So this was our u prime, and this was our e to the u, if you're looking at that formula. Okay? Number 2. A, a quickie. If y is e to the x, what is y prime? Well, y prime is just e to the x, right? What if y was e to the 2x? This is part B. Then y prime would be derivative e to the 2x. C. What if y is e to the 5x? Well, y prime would be derivative 5 e to the 5x. What if y was e to the negative x? Y prime would be the derivative negative 1 e to the negative x. Not too bad. Number 3. G of x is equal to e to the 2x minus 1 all over e to the 2x plus 1. Okay, we've got to use the quotient rule here. Okay, so g prime of x will be, start at the top, take the derivative. Well, the derivative of e to the 2x minus 1 is 2 e to the 2x. The derivative of negative 1 is 0, right? Times your bottom minus, now the derivative of the bottom is 2 e to the 2x plus 0 times the top all over the bottom squared. This would be say stop. So if it was on a free response question, you would stop there. However, I see some things we can do to simplify this. So if it was multiple choice, we'd have to keep on simplifying. I'm going to distribute So 2e to the 2x times e to the 2x. You add your exponents if your bases are the same and you're multiplying. So 2e to the 4x plus 2e to the 2x minus 2e to the 4x plus 2e to the 2x all over that bottom squared. I'm not going to do anything with the bottom. The e to the 4x's cancel out, and we have 4e to the 2x all over e to the 2x plus 1 squared. So this would be the multiple choice answer. Okay. Just a couple more examples. Number 4. Okay, let's say that we have this equation and we want to find dy dx. So hard to solve for y, so we're going to use implicit differentiation. So I'm going to take both sides, take the derivative with respect to x. Okay. For this first piece, I need to be sure to use the product rule, right? Product rule. So the derivative of x times, keep your e to the y the same, plus, now I'm going to leave my x alone, take the derivative of e to the y with respect to x. So the derivative of e to the y is e to the y, but then we need to multiply by dy dx. Minus 10 plus 3 dy dx, and that's going to equal 0. Okay, I'm going to take my two dy dx terms and factor out a dy dx, and anything that does not have a dy dx I'm taking to the other side. So this will be 10 minus e to the y. And now just divide both sides by whatever is with your e to the y. I'm sorry, whatever is with your dy dx. I was looking at that. Sometimes I can't talk and write at the same time. And I don't see anything else that they could do to that. You definitely would not cancel out the e to the y's, though, right? That would be a no bueno situation. You can only cancel it out if it's in every term and you're factoring out and then reducing. This term does not have an e to the y. This does not have an e to the y. Can't do it. All right, number 5. What about this one? Y is equal to 3 to the 4x squared. 3 to the 4x squared. It's not an e, it's a 3. If it's not an e, I know I need to multiply by that ln of 3. Multiply by ln of whatever that base is. Okay? And then you treat it like an e to the 4x squared. So treat it like it. So if I was treating it like that, I would have the derivative of the exponent times 3 to the 4x squared, right? That's it. Make sure you use parentheses here, you guys, because without the parentheses, it would look really, really wrong. Let me remove my parentheses and see what you mean, see what I'm talking about. That totally lost meaning, right? Well, it lost our intended meaning. So be sure to use parentheses around all your terms. You can rearrange the order here, but it all needs to be there. Okay, number 6, last one. F of x is x to the 2x. Find f prime of x. Well, little product rule. So f prime, derivative of x, leave your 2 to the x alone, plus, now I'm leaving my x alone, and I'm going to multiply by the derivative of 2 to the x. So the derivative of 2 to the x, start off with your ln 2, and then treat it like an e to the x. So this is just 2 to the x. Okay. Again, you guys, the derivative of 2 to the x is ln 2 times 2 to the x. The derivative of 5 to the x is ln 5 times 5 to the x. The derivative, you can think of this, the derivative of e to the x is ln of e times e to the x, but ln of e is just 1, right? So that's just e to the x. Alright, that's it. It's a little bit of a shorter one today. There we go.